copy 8255 near Phoenix? This is 8255. I think I did hear you, man. This is 8255. Do you copy 8255? I think I did hear you, man. From 8255 Phoenix. I definitely hear you in there. This is 8255 Phoenix. I heard you in there, man.
Somebody shut this guy. Alright YouTube, hello, thank you for watching. Today I'm building a support board for a 25 meg oven oscillator. This may be something that's going to be used in a radio project. I'm not sure if it's going to work out for that or not. This is why I got some extra space down here at the bottom, and the board is kind of irregular shaped. My guess is this will probably take a couple hours, I think. So step number one, I guess, is get a connector on here for power and ground. This runs on 5 volts DC. This is a 25 meg ocxo. Should draw about 600 milliamps during oven heat, and then it probably will drop off to about 100 and some milliamps. So I'm going to power this with a Motorola 7805, and there's going to be a voltage regulator on here to adjust the trim frequency, which is going to be an adjustable regulator. The output on this oscillator here is actually a sine wave. So usually what I do then is try to establish some kind of ground points, although I probably have said this a million times in my videos. It requires a lot of read-ahead comprehension. Sometimes you lay things out and you start to lay them out in one way, and then you realize because you can't fit the other components in where they were supposed to go because of something you put there. Now, I don't have to isolate the heatsink on this because this is a fixed regulator, so the center lead of it is ground. There may be some point where I have to take this heatsink back off to get stuff in there, but I want to have the heatsink on. That way I can get a good idea what space I can use and which space I can't use. So our reduced 13.8 comes onto the input here, and then the output is 5 volts, which goes over to the ocxo. These resistors here just drop the 13.8 down to a level that'll pull some heat dissipation off of this. If you ran 12 volts into this regulator directly, this regulator would get much hotter. You can adjust these value resistors here, these droppers, to kind of equalize the power dissipation between this regulator and what's being dissipated by the resistors itself. So that's a total resistance of just probably a little scotch over 9 ohms. So it's 600 milliamps. We're going to be dropping like 4 or 5 volts across there. 600 milliamps times 9 ohms. Yeah, we'll be dropping 5.4 volts. So that's 5.4 volts of potential power that's not going to be dissipated within the regulator itself. It'll be dissipated over here. I guess next we want to put this regulator in there. I think that way might work. There's going to be some other stuff at some point in time going on this board, so I need to keep this section over here as free as possible and take up no more space down here than I really have to. Going to be a 240. That's the feedback resistor for the voltage adjust. This small regulator is going to be nominal at 2.5 volts, and it's going to swing plus or minus a half a volt. And then I need 150 ohm, which is going to go from that adjust pin, which is the first pin on that voltage regulator. So that'll stick the pot up here somewhere, although there's no ground up there. That's what I said. Sometimes you just, things don't go in the direction they're supposed to. Well, I can get a ground, I just can't bust some solder wick over the board and tie it down. I just take bus wire, wrap it around the solder wick to hold the solder wick to the board. So when this pot's turned the whole way up, we want the most resistance or the most voltage, because that'll be adjusting the frequency up and down. So we want most resistance all the way up between this point and ground. And since that wiper's swung that way, most resistance will be over here on this terminal here. Now this has to bus over to ground. There we go. So we should have the most resistance with that pot turned the whole way up. Between here and there, we should have 355 ohms. So this voltage regulator will adjust, like I said, on center position of this pot, it's going to be nominally 2.5 volts, and then it'll slide between 2 and 3 volts up and down. At some point we're going to have to get some capacitors on here, but I'm not sure we're at that point right now. Now one thing I really should have on here is a diode, and this diode goes across this 5 volt regulator from the input to the output, the cathode of it to the input of the voltage regulator. So the diode goes that direction, although I might need one more hole here. So that diode goes across the input and the output of the regulator. Yeah, and this is the crazy stuff that happens here. I've said this before in videos. You get a whole shit pile of stuff on your bench, and you're just grasping at straws, reaching for stuff, and then the next thing you know, you're picking up a piece of bus wire trying to solder with it. And what that diode does is it allows a return path back across the regulator for when you hang a tantalum on the output of the regulator, because tantalums can really deliver a hell of a whomp of current because they have a very low effective series resistance. If the power supply line were to ever short, what would happen is that tantalum would discharge back through the voltage regulator. And voltage regulators don't like to have a tantalum discharging back through them. So the diode just bypasses that positive voltage from the tantalum cap that I don't have on here just yet, back towards the power supply around the regulator so it doesn't have to go through it. That's a 2.2. Now we need a minimum load resistor from the output of that one just out in, because you can't expect a voltage regulator to regulate right if it doesn't have some sort of minimum load on it. And the input voltage adjust pin on this doesn't provide any significant amount of current to be drawn off the regulator, so you have to tie the regulator to a load, which in this case will probably be around 10 milliamps or so. You don't need a lot of load on it, but regulators do need a minimal amount. Now we really don't need one on this regulator, but I'm going to put one on anyway. So in ground out, kind of like so. Now also we need some type of minimal load on the output of the ocxo for testing. I don't ever leave things float. Things always have to be tied one way or another. So I'm just going to hang a 10K off the output of the oscillator, and it'll be connected to a frequency counter to see how this oven oscillator is going to work out for me. I might need like a test jack on it just to make things a little bit easier. It would be nice to have an SMA on here if it doesn't eat up too much space. Here's a piece of junk Chinese one. I kind of see a hole jumping out at me here. Although these are made to go over the edge of the board. Just run a piece of wire wrap down from the output of that oscillator onto there. We need a wire going from the output of this regulator over to the voltage control pin on the ocxo. As far as I know, all done. Got some chip caps on, some electrolytic caps on.
Pennsylvania. Nice to hear you. What part of Pennsylvania? Gorgeous. 77. What part of PA are you in? Oh, my memory, when you get older, your memory just goes. You just told me you was Valley Forge. I got it.
Guy asked him what part of Pennsylvania he's in, and then the guy tells him, then he says, "What part of Pennsylvania are you in?"
747, Eugene, Oregon.
Took 5 hours to build this. Don't let the simplicity of something give you a false impression of how much time it's going to take. That's all I can say. It's time consuming. So essentially what I've done here with this board is I've just made another one of these, only this one here is a 10 meg of an oscillator and this one here is a square wave output. Well, it's drawing about 600 milliamps. Let's just double check this regulator here. We should see about 2.5 volts. Oh wow, that thing cut back. Never saw one do that before. That thing's like roller coastering to level out. Usually they cut back all at once. I never saw one do that before. Should draw, I think, about 150, 160 milliamps at idle. And I would say that's probably pretty much idle there, because the frequency's pretty much stabilized. This one here come up really quick. It's warm, that's about it. I didn't realize this oven would come up to temperature so quick, otherwise I could have probably got away with smaller dropping resistors here. So there we are, 150 milliamps. I might need to change this voltage regulator to trim this on because there's plus 100, there's plus 42. I kind of figured this oven oscillator would be on frequency at 2.5 volts, but it looks like it needs to run lower than 2. Let's see what this one says. I didn't calibrate this counter on today. Normally this counter sets idle, and sometimes the oscillator adjusts pot in here, shifts plus or minus 10 hertz with, I guess, the dirt in it. Well, you learn something new every day. I asked the guy that I bought this counter from if he calibrated it. He said he checked it against a Sencor unit that came back from calibration or something, but you know, what does checked it against it really mean? Either you calibrated it or you didn't calibrate it. I would say this 225 meg counter needs a little TLC. What I'm going to have to do here is just shift this pot. Right now, center of this pot is 2.5 volts. From what I'm seeing here, center of this pot needs to be more like 2 volts, plus or minus a half. I mean, that's cool. I'll just get the calculator back out. Calculators are an addiction for me. Hey, thanks for checking out my video. This project is still classified. You may see this pop up in another video and you'll say, oh, that's what that guy's going to do with that thing. So hey, you take care. You have a great day.